right, let's get to resonance, and this will let us talk about the Tacoma Narrows Bridge in class next week for week 9, which is pretty fun. So we're going to talk about resonance and musical stuff first, and this is the last section in our week 8 package, which is week 8 resonance, and why do I have to keep blowing into my bottle flute if we said there's a standing wave? Okay, so that was one thing that we did that in class that seemed to register with people, and that is if I send a pulse wave, oh, my amplitude has to be something, I'll set it big. If I send a pulse wave down, I can make it get bigger. Reference line here. I can make it get bigger by sending a pulse wave with it, by adding a pulse wave with it as it comes in, okay? I can keep adding pulses to it. This was a good lead into our constructive interference. This would be an example of constructive interference. If I wanted to make this destructive, I would send it above when it was below. It's harder to do with this setup, but I would send it in opposite directions. So that's a good example of constructive interference. Okay, so let's restart it. And we have a certain wave, certain pulse wave. Let's make it go. Oh, let me restart. I want you to think about the timing that I'm using. To do this well and to do it right, I have to do this at a certain rhythm. If you can hear, I don't know if you can hear my mouse clicks. Okay. All right, so there's a certain frequency with which I'm clicking that mouse button to get that pulse to go up. Okay, this is another thing when I ask you to stop and do the thing. So there's a certain timing that I have to use. I have to get the timing right to get that to go. So the frequency, the number of times I could take the number of times you hit the pulse button, and I could watch. If you were doing this, I could watch you for a minute. If you were doing it successfully, I could watch you for a minute. I could count how frequently you hit the button. I could divide this by 60 seconds and get your average frequency per second. Now, if you go to our definitions in the packet below, waves have a frequency, and that frequency is how long a whole wave takes to go past a certain point. And it is also measured in 1 of anything per second. Notice that we measured something per second up here. Since you wanted to go when the pulse was high, you want to add when the pulse was high, you are also, when you're doing this, waiting for the same part in the wave. So you are clicking this at the frequency of the wave. We call the frequency the wave is already going in its natural frequency. And what I'm doing to get it to resonate, this is resonance. What you're seeing here is resonance, is I am clicking my button at the natural frequency. If I clicked it at the perfect natural frequency, you'd see a beautiful resonance. It's a little bit sloppy. Resonance adds to amplitude. Amplitude is the height of the wave from equilibrium. So you see this is so high it's off the page. This is what resonance is. If you've heard of the term resonance, resonate, that's what it is. Okay. So what I want you to do is, in another part of the homework, is to get some resonance going. And then this system, don't add very much damping, just add a little bit of damping and it's going to dampen pretty quick. In order to keep my standing wave going, I have to keep adding energy to this thing. So we had a standing wave, but we had a standing wave with no damping. In reality, we have damping. Damping is caused by the friction of the media. It's either, if it's a water wave, it's water molecules against each other. If it's air or sound wave, it's air molecules against each other. That friction causes this, sound doesn't go on and on forever like light does. This is a hint for what's ahead. So when you add that dampening, you have to keep adding energy to it. In Glenn's homework, when he made his bottle flute, he set up a standing wave, and the wavelength was determined by the height of the water in the bottle. It's the physical length. This, you can visually see the wavelength. There might be multiple nodes, but this is related to the wavelength. Okay, when you blow across it, some air comes in, it goes down to the bottom, a wave of air goes down to the bottom, it bounces back. Now, how does it set up a standing wave? If you just blew one, into it, it wouldn't set up a standing wave. It would just go down, bounce back, bounce out. The way it sets up a standing wave is it has to reflect back. Notice that this reflects back at this point. Hit restart. It reflects, it reflects. So to set up a standing wave here, we have to have some sort of reflection. As Glenn keeps blowing, the air moving across forms something that some of the air will bounce back to, and it will bounce back here. The part that is the standing wave will get amplified. The part that isn't the standing wave won't be amplified. It will it's like all these errors. When I try to make my resonance happen, I get these little messy errors that don't look like a perfect thing. But as I get my resonance more and more, those errors will be less compared to the standing wave. And that's why we hear a clear, singular tone and not a bunch of tones. So there's a little thing in the packet that just says that, yes, air can bounce off, moving air. It doesn't do it perfectly, but this is part of why people were very surprised to find that it is usually more aerodynamic to keep the tailgate up on a car. So you don't really need to know that for waves. It's just a kind of cool little physics thing. All right, and then the rest of the packet is just reviewing the definitions. So you are done. Go do the simulations, and you will be finished with the homework. All right, sorry about the lecture, but thanks for letting me know that things weren't really working. All right, talk to you soon. Bye.